Actually, not real. It's for the baby, but it's not really good. It's really is
Mine is just, see.
Where do you guys go?
You go to, Dragonstone brand. Yeah, you should.
That's like, wait, not relax. Really overwhelming. Oh, but.
Or you guys keep bacon. I'm gonna eat my fingers with this.
Banana. The fetus is what they got being.
I love banana.
I don't think I think of if you think something like
Where are you going?
No, so.
These pencils freezing.
I'll probably go to the library. Is it wrong?
How are you?
Isn't that right?
Your kids are fun. Hospital. Oh, yeah. Oh, yeah.
What?
Alright. Good to go, Gary.
Okay. Well, happy to be back again. So we were, yes, the first lectures I dealt with gas chromatography, and last lecture here was looking at mass spectrometry. And so we spent some time looking at how you interface a gas chromatograph with a mass spectrometer. Gas chromatographs have fairly low flows of gas, into this high vacuum region. And it's always a problem. How do you maintain that vacuum? You must have a vacuum. If you don't, all the ions you want to measure, they collide with air someplace or some other gas and you don't get anything. So having a really good vacuum is extremely important. But with GC, or gas chromatography, that's relatively simple when it comes down to HPLC, the high pressure liquid chromatography, high performance, whichever it's called. In that case, you're dumping a bunch of solvent that comes off the HPLC and trying to dump that into a high vacuum. Solvents, of course, are volatile, and they just kind of blow into a really large volume. That's tough to deal with. The mass spectrometer can't deal with that. It must operate under a vacuum. And so that's where we get into different types of what we call sources, or atmospheric pressure, chemicalization, electrospray, thermospray, electron beam. So a number of different ways we do the atmospheric pressure, different ways that we manage the volume that we get out of the system. This is the most common way of getting rid of HPLC liquid. So when we think about there's our ESA nozzle over there. And that's actually where we're going to get our volatiles that, notice this, the solvent is volatile. And so when you simply dump it off of your LC, it will get vaporized or sprayed and vaporized. And that solvent tends to then evaporate, leaving ions behind, or the molecules behind that come from the samples you're analyzing. So this is one way, and your sample does come in that side, and it hits this the electron dense area, makes things basically evaporate in the process. So that's our way we separate our liquid carrier from ions. That's, like I say, the most common. There's other types of ways to separate our sample from that liquid coming out of the HPLC. And this is atmospheric pressure chemical ionization. This is not done under a vacuum. It's done at atmospheric pressure. And it's very much the same in this sense. We come across on this side from the capillary, whatever our liquid HPLC is dumping into the system. And it's under atmospheric pressure, but again, there's a corona, there's a needle giving us a good deal of charge up there. We get charges that get drawn into the mass spec where we separate our masses, count our masses, and figure out what the heck that we've got there. When you look at the output from HPLC, the top figure up there is just more or less a sum of the ions that are coming in. So different peaks, different components. There, hopefully, your sample is in there. What you're looking for happens to be in one of those peaks in across. And the mass spectrometer just keeps on sampling. And so what you see coming down in this case are basically the MS profiles. So the mass spectrometry profiles coming across. And like I say, they're constantly taking sampling of the eluent from the LC. There's different ways that you can do this or use this, and it's kind of interesting that sometimes often, most of the time you want to do quantification, but how do you do quantification? And one way with the mass spectrometer is making a deuterium, a stable isotope of the compound you want to measure. And so it's rather interesting. You can make a reference compound that's this identical molecule that simply has had a little more charge put on it. And so it's really a nice way to do this is you can, like say, use the same compound that has some deuterium to monitor your compound that doesn't have deuterium. So the mass spectrometer is kind of following this along as it goes through the run. This is a spectrum of dimethyl derivative of fluoroacyl in blood plasma. I have no idea what that is, but anyway, it was given as an example of taking profiles. So mass spectral profiles of a sample and an N15 standard. So the top one doesn't have the isotope. The bottom sample has been labeled with an isotope, and this sees only the compound with the isotope. So again, it's nice to be able to separate the two and do your counting. And this is a purity of peaks. Let's see if I went right. Measure components in a mixture. It's interesting that you can get profiles again of many compounds at one time. So whatever's coming through, you get a profile of. If you can get the parent ion, you know the molecular weight of that compound that's eluting. And you can actually quantify, again, materials without separating them. And so it's, again, a fascinating component to LC-MS. This is another takeoff on that. How do you quantify a compound when it coelutes with compounds of equal mass? In that case, you are taking spectra, and you don't have to isolate, you don't have to separate two compounds. You can isolate the spectrum for one compound, isolate the spectrum from another compound, and simply monitor those ions as it goes along and draw your separation or your peaks and peak areas. And so again, another choice or another benefit The big pain in the butt with this is all the solvent you dump into there, but there's a lot of benefits that you can get out of this type of chromatography or mass spectrometry, perhaps I should say. This is a triple quad, so that's where you have actually 3 separate units where we try to separate the ions that you generate. So say you blow your sample apart, you have lots of ions, and then you want to separate them, count the ions. And so based on what ions you see, it can only be a certain compound, hopefully. So not 2 that match, but hopefully one that goes. And these quad Q1, quad 2, quad 3 are just really improving the separating ability of these ions that you generate. So again, you measure what you think you're doing. Cost $250,000 and up. That's probably pretty hard to get one for $250,000 these days. So a pretty hefty price. But again, they do a lot of things that are hard to manage otherwise. So, well, and give a couple examples, I think, that should be coming up. Lab problem at the moment, we want to determine measure compounds in the presence of soy protein, originally and after texturizing. So again, we were taking a look at what's in this system for volatile compounds. And one approach is we can use a purge and trap. We can do gas chromatography, purge it, trap the volatiles coming off it, do gas chromatography. But we can also do some of these things by liquid chromatography, so we can measure some of the same compounds. This is I was going to say crummy slide. It's not as clear as I would like, so this is a little on the frustrating side, but it's actually better than I thought. Looking at my screen, I decided I wouldn't be able to figure it out, but so that's a fairly decent shot. And so this is what, if you're going to go down and take a look at mass spectrometry, give it a shot down there, you would get a printout of this kind of, I guess, this composition. And so up on your upper right, you would find that's the MS trace. That's a total ion trace. Here comes a compound, another compound, over time, they're eluting from an LC or a GC, either one. And so you're going to draw what they call a chematogram. And that gives you an idea of the size of the peaks, the difference in molecular weight of these peaks, volatility to some extent as well. So you get something to look at up there. It's nice. It gives you a feeling for, okay, this major components, minor components, and so on. That's kind of good. It also these days has the ability to do some of this work for you. And so there's this chart down here. That's each line across is a single chemical. And so that's a component. We've gotten the mass spectrum of it. The machine is compared with that fragments, but blows up the bits, looked at those bits and said, this is most likely octanoic acid, nonadal, whichever carbonic acid up there. And so it takes those pieces, like I say, and it fits them and says, this is what it thinks it is. Since I thought this was going to be a crummy slide, in other words, not clear, I blew it up, and we'll take a look at the pieces that are a little better to view. So that's your chematogram. And that can come from either, a GC interface or LC, liquid chromatography interface. And so what you'll always get is you get time, that's across the x-axis, you get intensity across the y-axis, and the machine will integrate the area under each of these peaks. And the area under the peaks relates to quantity. So we're getting basically a measure of quantity when we look at these chematograms. And I probably didn't improve it much. This kind of looks like the other one. But the next slide, I've actually blown one of these up. So like I say, the machine goes through and does this for you. It takes everything, matches it up to what's in its library, and says, this is what you've got. This is exactly that previous table, but something that's a little easier for reading or understanding. And so in this particular sample that it showed us, I selected only 3 compounds. One, at least, where we get a retention time and elution out of the instrument of 24.1915 minutes. The machine takes a look at all the pieces, those fragments, and says, hey, those fragments fit dodecanal. So it tells you that compound, that's peak, is dodecanol. It then just says, how good is its guess? And that's the next one, a match factor. So how good does this profile of bits and pieces, masses that it blew up into, how good is that match of your sample to the reference, to a standard? And it can go maximum 100% match. This is 97.7 for the dodecanal. The base peak, it gives you what's the most abundant fragment. And that's your base peak. And that's a mass of 57. So that's useful in terms of identification, is having that base peak. This also does something else for you, which is really helpful, is that you have your retention indices. And so we typically will make a run on either the MS, the GCMS or the LCMS. You put your sample in there and you can get, okay, a retention time and, like I say, bits and pieces. The retention time is also important. We try to match by the mass spec by the pieces it blew into, but we also try and match in terms of retention time. And so what we find up here is match factor, base peak. Now, the component R index is where we put reference hydrocarbons. So we'll do our, let's say we're doing GC. We've got our sample. You don't know what it is. It's over here in the solvent. What we do is we add hydrocarbons. Hydrocarbons 6, 7, 8, 9, 10, and molecular weights are going up. One carbon at a time. And so we actually spike our sample with a whole series. So let's say decanal, dodecanal, and so on down the line. So we have pure reference compounds, and we calculate where between that reference compounds does it come. And the top one up there, a component R index of 1421, means it comes out just after the 14th hydrocarbon. And so that's something that is based on, of course, the GC or the LC separation, but that's what our compound is. That's where it comes. And then we can go into a library, and most of these things are published these days. And the library says, well, dodecanal, according to our experience and data, whatever, should elute just after the 14th hydrocarbon, 0.09 distance after it. So what it is it's a reference, and it tells us when our compound elutes compared to the reference. And the delta Ri on the top then says, okay, how close is the elution time? So how close is the elution time to the published value? So we see a delta Ri up there of -12. That's 12 units difference, 1409 to 1421. And we'd look at that and say, that's pretty good. So we've got the bits and pieces. We have all these fragments that we get to look at, match them up, and we get elution time against standard. So we've got two different metrics, the retention time and the fragment ions. And so this one here says, well, that looks pretty decent, minus 12. Second compound, dibutyl phthalate, eluted quite a bit later. You come across that library index compared to the published data, 1956, 57, I'm sorry, is what the elution time for our compound in our system was. What is the published value? 1965. And so that's within 8. You can look at that and say, great. We have another compound eluting in this mass that I showed you. That's 1 decanal. And that's what the compound, the best guess is a match of the same 97.5. And so we kind of look at that and say, well, that's a good match on the mass spectrum. But we kind of look over here, and the component R index is 1586. It says it elutes after hydrocarbon 15. But our compound comes just after hydrocarbon 13. So it can't be. Great match. Machine tells you it's this, and it isn't that. And that's where you come into the system. You kind of look at that and say, that can't be. So the identification is wrong. Maybe the spectra wasn't very good. Maybe there's only a very small amount of sample. There wasn't a lot of ions to separate from the garbage in the background. Something went wrong. And that's what basically this machine does, is it looks at, or the process is, double what are the pieces it flows into, where does it elute and compared to literature values. And so the machine basically gives its best guess. And so this is, again, what you would like to do and should do is go ahead and here's the spectrum of your compound. Here's the spectrum of a compound you suspect it to be. You also take a look at that. So you don't make mistakes. You check on the machine. The machine will give you an answer. It'll always give you an answer. But that doesn't mean it gives you a right answer. That's where I kind of harp on the idea that know what you're doing, know what your machine does, know the limits of that machine. And so, again, the person can go through this kind of profile and say, yes, it looks good, or no, it doesn't. And again, out here, we've got a fairly decent sized mass up at 140 that isn't present to the same extent down here. It's close, but not quite. We got a 156 out here that doesn't show up there. And so that's not a particularly good match. And so, again, the idea is pay attention, check on your machine. The machine isn't necessarily flawless. So this is a different example, but it's kind of going the same direction. In this case, we're looking at the 3 compounds and 1 below it. So again, if we go through the data, the match factor, they're all good. Areas, that depends on how much is there. So that's, you want to know that perhaps, but that's not helpful in terms of looking for a good fit or correct fit. In base peak, the base peak, that's again your most abundant ion. And you also consider that when you look at it, the spectrum and try to identification. What's the most abundant? Is it a good fit? Is it what it should be or not? And then here's your fit for the compound retention index library. And in this case, of these 3 example compounds I just picked out for you. The first one, the delta retention index over there, minus 12. That's really quite good. It says it elutes just after hydrocarbon 14. Another one's a little closer to the beta, to the carbon 14, delta Ri minus 12. The next one is a delta Ri of 8. If we look at kind of this final tabulation, there's a compound out there that it misidentified, but it caught the misidentification up there. The MS said it was something, but the retention time simply can't be.
So what's kind of the critical delta then for when you would reject what the compound gives you?
Sure. So what do you expect up there? In terms of what would you accept? All these things take some judgment. There may be a case where you're fairly lax because there's other good data that says it may be right. But the idea of being, I would say plus or minus 20 is still pretty comfortable.
Like 100 would be definitely too much.
Well, that'd be bad news.
Okay.
Bad news.
Please, like,
Yeah,
okay.
that's, probably not correct. And then you go in and take a look at it. Maybe it's not of interest, so you say, oh well, so for that. But if it's really what you're interested in, you're in trouble on number 3. So again, the machine does this for you, but it's up to you to interpret it and say, what did it give me? How much leeway will I give on that? If it's a really strong spectrum and you look at it and say, no, I can't find any differences in here. But still, you couldn't live with that difference. 1371 up there. No, that's more than you could live with. So again, that takes just kind of practice in trying it. Resolving issues with data. It's amazing what you can find in the literature. You may be interested in looking for a certain chemical compound, a flavor compound, a toxic compound, whatever. You can go to literature and you can find a great deal in literature. So you can find spectra of that compound. You can find a retention index. So if you don't have your own spectra, you can go to literature and get them. And again, then you could simply do comparison. I like machines, but I also like people a great deal. I do. I think we're smart most of the time. But the machine doesn't necessarily have that ability. So this is just looking at some other spectra in a situation where you kind of look and say, what compound is this? You're unknown, so that comes from your run. So you find the middle one. And then the machine says that 2-vinyl furan is really quite similar. Well, that dimethyl sulfide isn't too bad either. It will list the machine's first choice, second choice, third choice, and so on. And again, you look at them. Because if you don't get perfect separation in this run, you've got a peak coming here. Oh, that's the one you want. Right next to it, they're a little bit mixed. And so you get a little carryover. Things don't work out right. So again, it's a time when you sit and kind of look at where is it solution time? Is it eluding with something? Where do you put your data? What do you believe? So we've got 2 very different, or let's say similar compounds in terms of chromatogram. So mass coming across here. And you look at this compound, dimethyl disulfide has a fragment at 79. Your unknown has a fragment at 79. Isn't the same proportion, but they are also there. And look at the other section, 45, peak here, a 65 is down here, that's a 66, 65, 79, 79. You would go along and say it is dimethyl disulfide. So there's, like I say, the machine does this, but you still need to have ability to do that. This is just looking at another compound. So our unknown is up at the top. The machine says it could be pentanal or it could be 2-methylbutanal, 2 fairly closely related compounds. Both 5 carbons. And again, you look at that profile. There's a good deal of similarity. We got major peaks here, major peak here, 29, 29, 44, across the top, but there happens to be two up there. So we'd see two peaks around 43, 44, mass 44. Good agreement here. This one, this one has 71, but that's not. Well, it is up at the top. Okay, 71, 71, 86, 86. Basically, here's where you get your differentiation, which agrees best. So I guess my concern or whatever is that it can be a difficult determination. It's really hard when the sample is very low, you don't have much material. So you don't get good spectra. There isn't enough of your compound there. So if you've got a fair amount of compound, you get a good spectra, you get a retention index. It's still a little bit of human intervention in the system. But again, we've certainly come a long ways over time in terms of getting this far. If the identification is extremely critical to you, you probably would back that up again. You'd maybe get some pure standard. And so you'd spike your sample with a pure compound. So you know there's the pure compound there. And did that peak that you suggested is there, did it get bigger? And not kind of bigger, but bigger, sharp, clean chromatography. Published retention data, that is funny. People all over the world contribute to these, and we look at them and say, oh, okay, I'm always happier if we get our own. How's that? We use our equipment, we get our retention indices, we get our data from it. It surprises me actually that we do as well as we do in terms of matching chromatograms and mass spectra. But it's a very powerful tool. There's lots of applications that it is used in. My work most recently looked at interaction flavor compounds with proteins. And so if you put vanilla flavor into something that has protein, a food that has protein, vanilla reacts with the protein. They chemically bond with each other. It may well be interested how much they bond, because there goes my vanilla flavor. And so the idea that flavor protein reactions occur, how do we understand them? What would they react? How fast do they react has been some of my interest. There's has been, and maybe less recently, aroma release in the mouth. If you're interested always in flavors being released, if they don't release when you put them in your mouth, so you get the olfactory, you get the taste, you don't know what you got. So again, there's been probably 15 years, 20 years, there was a lot of focus on, do we understand how flavors are given up in a food so they are sensed? And the mass spectrometer has been a real benefit to that, because you can put the mass spectrometer up your nose, not literally, and you will get that kind of data. There's vanilla flavor in my food. What do I sense? Identification of unknowns in a food, and they can be looking for adulteration is someplace. So that's down at the bottom. Flavors are expensive. Many of your food ingredients are expensive. Are you getting what you pay for? Is it something that's close? And again, mass spectrometry does well at differentiating adulterated products. Quantification, assurance of purity. It's really an extremely useful technique to us. Or looking, like I say, of looking at how flavor react with proteins. Our question was, how to lose flavor to proteins? We put the flavor into a protein-containing food. You have some very reactive chemicals that will react with the protein. There goes our flavor. So been a lot of effort looking at flavor-protein interactions. And it can be simply a loss of flavor, it can be a change in flavor, or it could be end of the shelf life of the product. Nobody wants to eat it anymore. And so the idea of looking at it with proteins was a rather interesting one to us. I don't know if there's a poster down the hallway down in food science or not. It might have gone away by now. But this is looking at beta-lactoglobulin as a protein in milk. And if we go ahead and put this in the mass spectrometer, we can get a fairly nice spectra. This is 18,300 molecular weight, 18,600, 18,900. And what we basically get is, here's beta-lactoglobulin. That's a little under 18,000, but it's reacted with lactose. So lactose reacts with protein. And so we actually lactose added on here. So our protein, one lactose is added, two lactoses are added. So we can look at how flavor molecules or other molecules will actually bond to the protein, because again, they're lost. They won't smell, they won't taste. This is one that's interesting to me. Benzaldehyde, if you smell benzaldehyde, it's cherry. It's a kind of a cheap cherry. Put a few more things with it, we can make it more expensive, or complete cherry. But the main component of the cherries happens to be benzaldehyde. And so in this particular case, we were taking protein. So there's pure protein up here. And that has our beta-lactoglobulin, our two lactoses added on. But let's go ahead and put a little bit of cherry flavor in this ice cream or in this beverage, wherever it happens to be. Well, what happens? That's just 10 minutes. So 10 minutes later, this was, time 0. 10 minutes later, we take that same protein benzaldehyde solution, and this is at the flavor concentration level, so parts per million of benzaldehyde. And all of a sudden the peak starts showing up. And that is the mass of the protein plus the mass of benzaldehyde. So you're looking at the molecular weight of that reaction product. And so that's only 10 minutes after this, you start losing the cherry flavor from the product. This is 6 hours later. Now this benzaldehyde reaction product is the small peak here. It's darn near as big as the protein itself. And so what we did is we basically took advantage of this methodology to look at how flavor compounds are lost. How is flavor lost from a food during shelf life or during storage? And so this is one, like I say, where most of the benzaldehyde will have been lost from the product by the time 6 hours had elapsed. Of course, then you might ask me, wait a minute, Gary, how long do some things sit on the shelf, and how does anybody taste anything? If it were all this bad, it is a problem, the flavor fade in the product. Fortunately, that doesn't take much benzaldehyde to give it flavor. And so you put in too much and it goes away and it becomes acceptable. So people actually plan on it losing flavor. And so it's more gentle. This another one where we were looking at replacing sucrose with aspartame. And so going from a bulk sweetener into a high potency sweetener. So how does the flavor different when you use sugar or use a high potency sweetener like aspartame, saccharin, and so on? And 3 different beverages were prepared. One had no sweetener, so these were beverages. The other was ice cream. And then we took our beverage. One didn't have any sweetener. Another sample set had aspartame, and another set of samples had sucrose, so sugar basically. Diluted to prepare 1 liter of beverage, so looking at stability of flavors in beverage products. And this is always kind of interesting. what we do in here is we were looking at how flavor is given up during the eating process. So between those three samples. And so this is the primary researcher. That's the beverage that was made with either sugar, aspartame, or nothing. And what he's doing is he's drinking this at the same time. He's got a little tube up his nose that's sampling his breath. So they're measuring what he's given in terms of a stimulus. So it's kind of interesting. And so, yep, there's the mass spectrometer behind. There's the tube that goes out and is sampling his breath. And you won't have to lose too much sleep over this one. But what you have at the very top up there, so the red line, that's actually him breathing. So breathing in, breathing out, breathing in, breathing out. And what it's doing is looking at basically the breath. So what's in the breath normally. The second one down, so that's green, that's what we call the swallow breath. So the first one up there, no sample. The second one, he's gone ahead and taken a sip and swallowed it. And he's still sitting there and monitoring. It's monitoring the breath. Where does this flavor go? How long does the flavor last in that perception? And we go through, increasing time as we go down the scale. It's rather interesting. These are some other compounds that you can look at too. So think about flavor release. You add flavor, is it released? Does a person actually get a dose for sensing? How much is the dose? How much is the stimulus that actually makes it where it needs to be for enjoying the product? This is, again, one of the most common applications of either GC or HPLC. How do you know the peak is one compound? And again, that's pretty simple in the sense that here's a GC profile of a pure sample. Suppose that you bought it pure, and there's up here 20 minutes is the major components. The other peaks tend to be some minor components of the whole thing. And again, it's a fairly simple way to look at purity of chemicals, monitoring, again, flavors. Are they bound to proteins? Are they bound to other things? Are they released for sensing? Do they make it into the olfactory region, the aromas and so on? It's certainly fascinating. It's made possible by LC and combining that with mass spectrometry. Adulteration, that's also another place where mass spec and particularly GCMS is used. You kind of look at undesirable components. What don't you want there? Well, look for substances added to food that are not natural or get contaminated, or food gets contaminated. Pesticides, contaminants, undesirable odorants, off-flavor components, and so on. So again, lots of use. Another use that I'm fascinated by is there's a company in the Twin Cities that actually does MS imaging. And so they bombard, you bring them something, and this happens to be 10 microns coming for the smaller one down here. And you can take that powder, and it's actually milk powder. And I crushed the milk powder and then had them scan for where my flavor is. So I'm scanning across this tiny particle and looking for my flavor. Is it in the circle? Is it diffused out? And so the redder areas are my compound. And it's pretty pervasive, but where it's darker, it's certainly more intense. So use it for imaging too, which is absolutely fascinating. Quantitative or qualitative analysis, identification of unknowns. Certainly, it's difficult to identify unknowns. There's over 10,000 aroma compounds that have been identified in nature. 10,000. And so if you want to monitor the profile of a food, that's a pretty good challenge. Fortunately, you don't have to get all of them. The majority of those 10,000 are there as trace amounts. So maybe you simply look at the top 50 compounds in there. But again, you're tying flavor, you're tying liking to an analytical profile. What makes a food taste like it does? What's released in the mouth, what survives storage, and so on. What makes a food taste bad when it goes bad? It certainly is a popular method. Cost has come down. At one time, only the rich could afford a mass spectrometer. They're easy to operate. I smile. I can't help but smile about this, about easy to operate. So I did my PhD at Penn State University, and I ran the mass spectrometer. That was my responsibility as a service to the building or to the researchers. It was funny at that point that I didn't tell you about this, right? Doesn't sound familiar anywhere so far. Good. But that was 1970. Okay. And things weren't quite what they are today. And so you had this machine with this big magnet. It's a massive magnet, and that's what bends the ions in the circle. And how in heck do you, in 3 seconds, get 200 data points printed out on the chart? And so you have a UV sensitive paper, and you have a UV light that, oh, here, this is happening. It just spits out about 10 feet of paper in 3 seconds. And that's basically what I did. And you sit down on the floor, spread it all out with a ruler and measure each of these. It was interesting. I'm glad we've kind of gotten over that. So it's a fun one. So costs has come down. Yeah, they're pretty much push button systems these days. Easy to operate, computerized databases, data handling. Again, you do that with some care. Certainly, they've become push buttons. And that's both good and bad. You should never think of it as a push button. You have to be involved with the instrument one way or another. So anyway, things have certainly changed over time. And gosh, I got done early. You keep them after then and just torment?
Do you want to?
No, I'm teasing. Anyway, mass spectrometry is come a long ways. And when you go down the labs, I hope you wander through the labs sometime, because you got I don't know, 4 or 5 of them, something like that down there. So, and if you're in this business, it's fun.